You know, uh, as unapologetic structural engineering geeks, we probably spend way too much time staring up at
Oh,
things.
absolutely. I mean, it's an occupational hazard.
Right. Like when you stand under a massive highway overpass, or you just tilt your head back to look at a skyscraper, there's this profound expectation of permanence. It feels absolute.
Yeah, it does. You look at that colossal gray pillar holding up, 4 lanes of heavy traffic, and it just looks invincible. Like the mountain itself is just sort of carved into that shape.
Exactly. But it's human nature to trust mass, right? If a material is heavy and dense, our brains automatically categorize it as completely safe.
Right. Which is funny because what looks like brute force is actually a highly calibrated, precarious balancing act.
And that is exactly what we are decoding for you today. We're taking a deep dive into the hidden engineering that keeps the modern world standing right above your head.
It's a fascinating journey, really. We're looking at a stack of structural texts tracking the evolution of concrete from ancient primitive mortars to modern pre-stressed marvels.
Yeah, and we're also going to look at the absolute core logic of something engineers call strength design. Because here's the secret. The material that serves as the literal foundation of modern civilization has a fatal hidden flaw.
It really does. And without some brilliant engineering workarounds, it would be practically useless for those modern skyscrapers and bridges.
So, to really grasp how we build the impossible today, we have to start with the fundamental nature of the material itself. Because concrete is not a modern invention.
No, not at all. Primitive forms of it, specifically lime mortars, were used as far back as 12,000 to 6,000 BCE.
Wow, that long ago.
Yeah, we see it in ancient Crete, Cyprus, and throughout the Middle East. It's been a universal building material for millennia.
And the recipe at its core is almost like baking. You take cement, water, fine sand, and, some coarse gravel or crushed stone.
Right, but the vital thing to understand is that it isn't just drying out like wet mud in the sun.
Yeah, it's a chemical reaction.
Exactly. The cement and water interact chemically. That reaction binds all those loose aggregate particles into a solid stone-like mass.
And that reaction requires strict management, right? Like a process called curing.
Yes, curing is essential. You can't just pour concrete into a mold and walk away to let it dry.
Just cross your fingers and hope for the best.
Right, no. If you want it to reach its full structural potential, you have to maintain very specific conditions of humidity and temperature from the moment it's placed until it's fully hardened.
Because if it loses moisture too quickly,
The chemical reaction stops prematurely,
mhm.
and you are left with substandard, weak material.
Okay, so assuming you've cured it perfectly, you end up with this material that is incredibly tough when you push on it or squish it. It has massive compressive strength.
Oh, it takes compression beautifully, much like natural stone. That's why it's brilliant for things primarily subject to compression. Think of classic Roman arches or thick, squat columns.
But that brings us to the fatal flaw we mentioned earlier. It is fundamentally a brittle material. Its tensile strength, meaning its ability to resist being pulled apart or stretched, is terrible.
It's practically non-existent compared to its compressive strength. Economically, you simply cannot use basic concrete for any structural member that is subject to tension.
I always like to think of it this way. Basic concrete is like a wrestler who is an absolute powerhouse at pushing an opponent around the ring.
Oh, I like that.
Right. But this wrestler has absolutely zero grip strength for pulling. If the match requires them to grab and pull, they instantly lose.
And in a building, pulling forces happen everywhere.
Exactly. If you build a horizontal beam out of basic concrete, as weight pushes down on the middle of the beam, it sags. The top gets squished together in compression, but the bottom stretches. It gets pulled apart.
And because concrete has no grip strength, as you put it, the bottom just snaps.
Which is why, in the second half of the 19th century, engineers popularized a brilliant partnership. They offset this massive limitation by combining concrete with steel.
They realized they could embed steel bars directly into the areas where that tension, that pulling, was going to happen.
To tag team the wrestling match.
Precisely. And it works beautifully because steel has incredible tensile strength, ductility, and toughness.
And the steel bars used for this usually have surface deformations, right? Little ridges and bumps.
Yeah, those deformations allow them to mechanically interlock with the concrete.
Yeah.
So as the beam tries to bend and the bottom tries to stretch, the steel grips the concrete and takes all that pulling force onto itself.
Boom, you get reinforced concrete. It combines the low cost, weather resistance, fire resistance, and compressive strength of the concrete with the pulling power of the steel.
It's the perfect marriage of materials.
But of course, human ambition means we always want to push the limits. We want to build longer, taller, and more daring structures. And as we tried to span greater distances, even that tag team ran into a wall.
They really did. The issue arises when you start using high-strength steel to support heavier loads. Standard reinforcing steel might have a yield strength of 60 kSc, but engineers started wanting to use steels with yield strengths up to 100 kSc.
Wait, before we go further into the weeds here, KSE, for you listening who aren't calculating loads every day, what exactly does KSE stand for, and what does yield strength actually mean mechanically?
Oh, fair point. So KC stands for kips per square inch. A kip is an engineering term for a kilopound, or 1,000 pounds.
Okay, so 60 KSE means the steel can handle 60,000 pounds of force per square inch.
Exactly. And the yield strength is the critical threshold where the steel stops behaving like a perfect spring. If you pull it past its yield strength, it stretches out and permanently deforms. It won't snap back to its original shape.
So if engineers have access to this ultra-strong 100 KSE steel, why is that a problem for the concrete? I mean, stronger steel should mean a stronger beam, right?
You would definitely think so. But as you apply those massive loads to utilize the high strength of the steel elongates. It stretches significantly before it ever reaches that yield point.
Ah, and remember, that steel is physically interlocked with the brittle concrete around it.
Right. So when the steel stretches, it forces the surrounding low tensile strength concrete to stretch too.
And the concrete just tears itself apart.
It induces large, severe cracks. Not only does the beam sag significantly, which is unnerving to look at, but those cracks destroy the durability of the structure.
Because moisture gets inside.
Yes, moisture reaches the steel rusts and expands, and the entire system fails. This stretching limit is the exact reason why building codes cap the useful yield strength of regular reinforcing steel. You can't use the ultra-strong stuff because it stretches too much for the concrete to survive.
So regular reinforcement hits a wall, the steel stretches, the concrete cracks. That sounds like a total dead end for modern architecture.
It would be, except mid-20th century engineers popularized a workaround that completely changed the landscape: prestressed concrete.
This is one of my absolute favorite engineering concepts, but I have to admit it sounds completely backwards when you first hear it.
It really does.
Instead of just laying the steel in the concrete and waiting for the building's weight to apply force, engineers actively introduce massive compressive stresses into the concrete before the beam ever sees a real-world load.
Right, they use high-strength steel wires or strands, and they embed them under extremely high tension.
They stretch the steel cables tight, pour the concrete around them, let the concrete harden, and then release the tension on the steel.
Exactly.
I have to play devil's advocate here because if you're listening to this, you might be thinking, wait, you're telling me we stretch the steel cables like giant rubber bands,
Right.
let the concrete cure, and then let the steel snap back to aggressively crush the concrete before the building is even open.
Yeah, that's the literal process.
Isn't that just fatiguing the structure before a single person walks inside? Like, why pre-stress something? You want to be resilient.
It seems entirely counterintuitive to assault your own building material, I know. But picture this scenario. Imagine you have a row of 20 hardcover books lined up on a table.
Okay, $20.
And you need to lift the entire row at once by only grabbing the 2 books on the far ends. If you just grab the ends and pull up, all the books in the middle immediately fall out. There is no tensile strength holding them together.
Right, the bottom of the row tries to stretch and the books separate.
Exactly. But if you push your hands together, if you squeeze that row of books incredibly hard from the ends, you introduce a high compressive stress. Now you can lift the entire row of books off the table as if it were one solid piece of wood.
Oh, wow, that is a brilliant way to visualize it. You are pre-compressing the concrete so much that when the actual weight of the building tries to bend the beam and stretch the bottom, it has to overcome all that built-up compression first.
Yes, the pre-squeezing fights the stretching. Because of this artificial pre-compression, the concrete on the tension side of the beam will only begin to crack at a much, much larger load.
It drastically reduces the sagging, and it virtually eliminates those tension cracks.
Exactly. This was the key that unlocked the ability to use those 100 KSI ultra-high-strength steels without tearing the concrete apart.
And unlocking that effectively unlocked the modern built environment. Once you understand that these structures are just clever manipulations of compression and tension, the architectural forms you see around you start to make sense.
They really do. We evolved from basic slab and beam floors to flat plate floors completely without beams, Just wide, smooth slabs resting directly on columns.
Or one-way joist systems, where closely spaced ribs distribute localized loads efficiently. But the true marvels of pre-stressing are concrete shells.
Oh, absolutely. Because prestressed concrete can be so incredibly strong, you can build roofs that are relatively thinner than an eggshell.
Some of the examples we reviewed are just wild. Folded plate roofs spanning 200 feet without a single column underneath.
Which is mind-blowing.
It is. And if you're wondering how flat concrete spans 200 feet, think of a flat piece of paper. If you hold it by the ends, it flops down. But if you fold it back and forth like an accordion fan, suddenly it becomes stiff and can support its own weight.
Right. The folded geometry creates depth that resists bending.
Hmm.
Then you have cylindrical shells providing massive, column-free interior spaces.
And the spherical shell in Lausanne, Switzerland, it has these sweeping, upwardly curved edges that serve to stiffen the central dome. It looks like a spaceship landed in the city.
It's beautiful.
Oh.
And of course, bridges have always been the ultimate testing ground for this material. Take the Napoleon Bonaparte Broward Bridge in Jacksonville, Florida.
Oh, yeah.
It is a cable-stayed structure utilizing a massive 1,300-foot center span. Or the Bennett Bay Centennial Bridge in Idaho, which is a massive four-span continuous box girder.
The one that really caught my eye was the Natchez Trace Parkway Bridge in Tennessee. It's a two-span arch structure rising 155 feet above the valley floor.
A classic.
Arch bridges are beautiful because the arch itself works entirely in compression, which concrete loves, but the flat deck carrying the traffic has to resist bending and tension. Pre-stressing that deck makes the whole system work.
And we can't forget the Dakota Dome.
Oh, the multi-purpose stadium in South Dakota.
Yeah.
Right, a 10,000-seat stadium. It originally had an inflatable roof back in 1979.
Right.
But by 2001, they wanted to replace it with a heavy steel roof. And they didn't even have to tear the stadium down. The original concrete frame and the massive ring girder were so durable and well-engineered that they easily handled the swap.
The adaptability is staggering. But
Yeah.
whether we're talking about a flat plate floor, a 200-foot folded roof, or a massive bridge over a valley, every single one of these structural forms is designed to fight a constant invisible war.
The war against loads.
Exactly.
The invisible enemies attacking our structures every single second. In engineering, these forces are categorized into three broad buckets, right? Dead loads, live loads, and environmental loads.
Dead loads are the most straightforward. They're constant in magnitude and fixed in location throughout the entire lifetime of the structure.
Yeah.
It is the inescapable weight of the structure itself.
So the concrete slabs, the floor fell, the plastered ceilings.
Right. And allowances for suspended piping and lighting fixtures. On a highway bridge, the dead load includes the wearing surface of the road, the sidewalks, the heavy concrete curbs. It's the burden of simply existing.
And engineers can calculate dead loads with high precision because they know the density of the concrete and the steel. But then we introduce human beings and the math gets messy.
Very messy. That brings us to live loads. Live loads consist primarily of occupancy loads in buildings and traffic loads on bridges.
They're transient. They're the things that move.
Exactly. They might be fully present, partially present, or completely absent. And importantly, their magnitude and distribution at any given time are highly uncertain.
We rely on specific organizations to define these parameters. For highway bridges, live loads are governed by ASHA, the American Association of State Highway and Transportation Officials.
And for railways, it's AREMA, the American Railway Engineering and Maintenance of Way Association.
But let's look at everyday buildings because the differences in live load requirements here are staggering. They are measured in pounds per square foot, or PSF.
Right. If you are designing a typical office building, the code dictates you design the floor for a minimum live load of 50 pounds per square foot. That safely accounts for desks, computers, filing cabinets, and a normal density of office workers.
But consider the real-world implications of this. If you are listening to this deep dive while sitting in a standard office building, the floor beneath your feet is rated for that 50 PS. But if your company suddenly decides to lease that floor to an archive or turn it into a library stack room, the code demands a live load capacity of 150 pounds per square foot, 3 times the load.
Which is a massive jump.
You could literally compromise the floor system because dense stacks of paper and books are vastly heavier than spaced-out office workers.
The fundamental assumptions of the entire building change based on occupancy. And if you are constructing a heavy manufacturing facility, that minimum requirement jumps to 250 pounds per square foot.
Wow.
Warehouses designed for heavy storage can even exceed 500 PS. You cannot just casually repurpose a commercial building's function without running rigorous engineering checks, because that specific live load capacity is baked deeply into the original concrete design.
So we have the dead weight of the building itself and the live weight of the chaotic humans inside it. The third category is what nature throws at the building: environmental loads.
Right. These are forces imposed by the environment. Snow loads, for example, vary wildly depending on geography.
Yeah.
Engineers actually rely on historical maps, like a very specific 1972 map of snow loads across the U.S. to determine regional requirements.
Then there is wind pressure, which doesn't just push against a building laterally. It can actually cause intense suction on the leeward side or the roof.
And earthquake loads. What's fascinating is that earthquakes don't actually pull buildings down. They create inertia forces.
The ground violently moves back and forth, and the massive weight of the building tries to stay still, which shears the structure apart.
Exactly. You also have intense soil pressures pushing against subsurface walls.
So you have gravity pulling the dead load down, chaotic live loads moving around inside, wind trying to push it over, and earthquakes trying to shake the foundation loose. Which brings us to a really profound realization.
Yeah.
Since human behavior is unpredictable and environmental forces like wind gusts are unpredictable, how does an engineer ever mathematically guarantee a building won't collapse?
That is the ultimate puzzle. And the solution is the ultimate safety playbook: the American Concrete Institute, or ACI code, and the mathematical philosophy of strength design.
Historically, engineers used a method called service load design, right?
They did. They essentially calculated the stresses a building would face under normal conditions and just made sure those stresses were limited to a safe fraction of the material's breaking point.
But over time, we realized that concrete and steel behave inelastically, meaning when they get dangerously close to failing, they don't just stretch and bounce back perfectly like a clean spring. They warp and yield in complex ways.
So the older method wasn't a true reflection of how a catastrophic failure actually unfolds. The industry shifted to strength design, and it all boils down to one fundamental ironclad equation of structural safety.
Okay, brace yourselves for the math.
It looks like this: phi Sn must be greater than or equal to U.
Let's break that down conceptually. On the right side of the equation, you have U. That stands for factored loads, or the required strength. This is the amount of force the universe is going to throw at the building.
But to figure this out, engineers don't just add up the loads realistically. They apply load factors. They artificially multiply the expected forces to create a massive, mathematically mandated buffer.
The classic combination you see in the code is U equals 1.2D plus 1.6L, meaning you take the dead load and multiply it by 1.2, but you take the live load and multiply it by 1.6. Why the massive difference in the multipliers?
It comes right back to the predictability we talked about earlier. Dead loads, the weight of the concrete itself, are fairly certain. A 20% buffer, that 1.2 multiplier, is usually more than enough to account for minor variations in concrete density or, slightly thicker slabs than the architect planned.
But live loads?
Right. Human behavior, temporary heavy equipment, a sudden unexpected crowd of people in a hallway, that is highly unpredictable. So the code forces engineers to assume the live load will be a full 60% heavier than the maximum they actually expect.
We mathematically overestimate the attack. But the genius of strength design is that it doesn't stop there. We go to the left side of the equation, the design strength, the building's defense, and we artificially underestimate it.
This is where the phi symbol comes in. Phi represents strength reduction factors. Let's say your math proves that a specific pre-stressed concrete beam can hold exactly 100,000 pounds before failing.
Okay.
You aren't allowed to use that 100,000-pound number in your final design. You have to penalize the material strength to account for imperfect workmanship on the construction site, slight variations in the steel's dimensions, or minor flaws in the concrete mix.
And the ACI code is ruthless about these penalties, depending on what part of the building we're analyzing. If you have a tension-controlled member, like a horizontal beam that will bend before it breaks, your phi is 0.90. You only lose 10% of your calculated strength.
Right?
But if you have a compression-controlled member, specifically a column with spiral reinforcement, your phi drops to 0.75. And if it's a column tied with other types of reinforcement, it plummets to 0.65. You are instantly losing 35% of your calculated strength. Why are vertical columns punished so much more harshly than horizontal beams?
This touches on one of the most critical concepts in structural safety: the consequences of failure. If a horizontal beam is overloaded, it gives you a warning. The steel yields slowly. The concrete cracks visibly.
The beam begins to sag noticeably.
Right. It is a gradual ductile failure. It complains loudly before it quits, which permits remedial measures. You have time to evacuate the building or shore up the ceiling.
But a column doesn't give you that luxury.
Exactly. Columns hold up everything above them. If a column fails in compression, it doesn't slowly sag. The concrete spalls off, the steel buckles, and the entire load drops instantly.
Wow.
It is a sudden, unexpected, catastrophic, and explosive collapse. Because the consequences of a column failing are so severe, often resulting in a pancaking structural collapse and massive loss of life, the code demands a vastly higher margin of safety.
We penalize columns mathematically to force architects and builders to make them significantly bulkier and stronger than theoretically necessary.
Exactly. We pad the stats on both ends to create an ironclad safety margin. We overestimate the loads attacking the building, and we drastically underestimate the strength of the concrete defending it.
And this padding isn't arbitrary, is it?
No, not at all. The load and resistance factors are derived from deep statistical models. Engineers map the probability density functions of certain loads occurring, and they overlap them with the probability curves of material strengths fluctuating.
So the exact intersection of those curves, the tiny sliver of statistical probability where an extreme load happens to meet a weak batch of concrete, is the structural failure rate.
Exactly.
Yeah.
And the ACI code mathematically calibrates these factors to aim for a probability of structural failure of roughly 1 in 100,000.
1 in 100,000. That is the invisible math keeping the roof over your head. So, to bring this deep dive full circle, let's recap the journey.
Let's do it.
We started with ancient brittle lime mortar in 12,000 BCE. We exposed the fatal flaw of tension and solved it with the partnership of steel reinforcement. We learned how engineers hack high-strength steel by prestressing it.
Squeezing the books together.
Right, squeezing the books to build soaring 200-foot folded plates and massive highway bridges.
We categorize the relentless loads attacking these structures. The constant weight of dead loads, the unpredictable chaos of human live loads, and the fierce environmental loads of snow, wind, and seismic forces.
And finally, we decoded the elegant, probabilistic math of strength design, overestimating the required strength and underestimating the structural defense to ensure we are all kept safe. Because the next time you park your car in a massive concrete garage or you stand under the heavy floors of a library stack room, I want you to remember something.
You aren't just looking at solid, invincible gray stone.
Exactly. You are standing directly inside a perfectly balanced mathematical equation of load factors, yield strengths, and tension control. You are inside the math.
That reality raises an important question, though, a thought we have to leave you with today. We discuss environmental loads and how the ACI code relies heavily on historical probability data, like that 1972 map of snow loads.
Or historical estimates of base shear, which is the maximum expected lateral force at the base of a building during an earthquake.
Precisely. So, since our highly tuned safety margins and structural codes are entirely anchored to historical probability data for things like snow accumulation, wind speeds, and seismic shifts, how will the ACI codes and the millions of concrete structures already built to those old standards adapt to a future where unprecedented extreme weather events become the new normal?
When the historical data that runs the math breaks down, how does the equation adjust? It's something to think about the next time you're standing beneath a massive overpass, trusting that solid gray pillar to hold true.